Right, so for those who didn't get to take a look at it, who didn't do the homework, let's take a look at this, right? Because they are all at you, right? Who? He did? Somebody are picking up. Hang on. All right. Who? All right. So what you see? Last day we looked at taking an alternating circuit, right? Take an alternating circuit and convert it to DC. And I told you that three main steps. Half-wave rectification, you remember this? Half-wave? Yeah. Half-wave rectification, and then full-wave rectification, and then after you do the full-wave rectification, we do something called smoothness. That's okay? How did we do the half-wave again? One diode, right? And how did we go from full wave to half wave to full wave? 4 diodes, right? Then the diode bridge. Yeah. And after the diode bridge, well, we did something called, I didn't show you that yet, something called smoothness, right? Right. So I want to explain here. I want to go over the way the I would like to go over and give you a note on the way full wave works. Yeah. All right. So those who don't have it, just take a picture of it quickly. Right, take a picture of it, and I want to explain what the red and the green represent. And well, you're supposed to write a note, but I guess how are they going to
Yeah, I know. I go. Let's look it up. Even examine in front of me, and I have to go that bridge. I was right.
All right. So what is here? I want to explain how it works, right? Oh. All right, so what is here? So we have an alternating supply, right? The alternating supply, right? I will write in a different color, right? All right, in purple. So we have an alternating supply, and we're trying to convert that alternating supply to this full wave rectification here. Real simple, right? We have a diode bridge. So you have to connect your diodes like this. I know last day I gave you the resistor outside here. It don't matter, right? It'll work the same way. Here's how it works. Whenever the alternating supply is on the first cycle, that's going this way. Here's how it makes sure that the resistor is receiving a voltage, right? The objective is to make sure throughout the entire cycle, right? The objective is throughout the entire cycle, you want a voltage to flow through this system. That's okay? And here's the way it works. It starts at A, and the current flowing to P. When it reaches P, will it flow through diode 1 or diode 4? 1. So it flows through diode 1. When it reaches at Q, will it flow through diode 2 or go through the resistor? Diode 2 is reversed, so it wouldn't go through diode 2, right? So it will flow here. When it reaches there, will it go through diode 4 or diode 3? Why? But remember why? Right, because it will always go towards the what? Huh? It will always go to the lower potential. Here is the lower potential, right? So it will go down here. It will not go back up to T2 and it will go this way. That's okay? So it will follow the red lines. Well, purple in this case. If I remove it, red lines. That's okay? So that means that look at the red line. Is the red line going through the resistor? Yes. So it means that whatever is happening here is flowing through the resistor. Now, when it switches now, I'll follow the screen out for you, going this way. When it reaches R, where will it flow? D3 or D4? It will go up to, sorry, D2 or D3? It will go up here. Will it go to T1? No, it will come here. And then it will go up to T4 because it goes from high to low potential. When it reaches D4, it will not come back here, it will go back here. Look at the resistor. Current flowing through the resistor? Yes. And it's going in the same direction. So whatever is happening here, also happening here, except it's not changing polarity, it's staying in the same direction. You're seeing that? So what that means is that we fully rectify the wave. Right? We took this and underwent full wave rectification. All right. Now we had to smoothen it out. But before we smoothen it out, take this note. Right? Take this small note. I am using this labeling, right? So if I had to change it. Your diagram was what? A, B, and C?
Yes.
Did I label this diagram the same? Good job. All right. What did I use? PV? Yeah. So E on top. E on top. B is here. C is here. D is D1. This is D4. This is D3. And this is D. All right, nice. Let's do my favor and label outside here TNT. Label outside here TNT. Right? Take this note. Okay, what the video of that thing? Give us the video without all. That's something you didn't have. Okay. Okay. You know what I'm saying? I'll beat this one. Where right for that? Right. Take this note. No, I'm not giving you notes. That was your homework. I give it. No. I have it, sir. Right. During the positive cycle. During the positive cycle, the current flows from P to E. Current flows from P to E. Right here, P here. P is on the outside. P is on the positive terminal, right? Full stop. When at A, the current flows to diode 1. current flows through diode 1. Since it is forward bias, to the point B, as in boy, to the point B as in boy. Then through the resistor, then through the resistor, to the point D. So at D, the current flows through diode 4. The current flows through diode 4. And not through diode 2. And not through diode 2. Since current flows from a high, potential at D to lower potential at C. High potential at D to lower potential at C. Question, right? How we know that A is a higher potential than C? How we know that A is a higher potential? By the way, based on right. So a plus is a high potential and a minus is a low potential. So A is closer to what? Positive and C is closer to 3. So it means that C is a lower potential. That's okay? So the current will flow from D to C. Right? Full stop. Then at C, when at C, it will flow to Q. When at C, it will then flow to Q. Q. Everybody okay with that? Yeah. So in short, it's going P to E to B to D to C to Q. So in short, it's going, right? We're going to put it in brackets. It's going from P to E to B to D to C to Q.
Well, so you can say that fast, right?
Look at that again. P to E, P, A, B, D, C, Q. Fab this.
No, you.
Fab this. P, A, B, D, C, Q. You read, right? Yes, you read. Right. Well, then, just do my favor to do your homework now. Can you write the other cycle?
Yeah.
When it's so next part of the line, when it is on the negative cycle, and finish it with comma. I'll ask somebody to read out their notes out loud. When it is at the negative cycle, it goes from Q to C. Right, finish the rest. Finish the rest. Anybody want to talk?
So you just say it's back.
What's for me? Right, finish the rest of the note.
Yeah.
We just do it, right?
And why? Just like look at the two file. Let's see what was up there next. What do you do on that? Huh? Alright, put the next thing. Do I have four? No, we don't. See, I was out. I was doing one. I thought we were doing better way. But we're not going to. Yeah, but I didn't know that. I'll listen to Shippy's notes. Right, I already told you what to do. You just put it in your own words, right? Yeah. WhatsApp. Anybody could remember? WhatsApp. No.
Every day until you're supposed to.
No,
yeah, we going from. Every day you got like a
Huh?
Oh, yeah.
Half 12 tomorrow.
So that might not somebody. Yeah, that's the phone number.
I was going
No, la ragazza sono tutte queste copie da
All right, let's go. Right, let me hear what you have now. Image, what you have? Image. All right, go ahead, Clara.
Okay, when it is on the negative side, it goes from Q to C. When I see the current flow through diode 3, such as forward bias to the point B, then through the resistance to the point D. At D, the current flows through diode 2, since the current flows from a high potential at D to a low potential at E. Then at E, it will flow to B.
Right, note that the current flows in the same direction to the resistor at all times. Note that current flows through the resistor in the same direction at all times. Sorry. It goes C to B. No, E to B.
Yeah.
Last part, you.
Exactly.
So when they went to the Americans.
Right, so what is the negative direction, right? It's going Q to C, at C, it's going through diode 3 up to P, and then from B, it's going through the resistor to D, and then D to diode 2 to resistor A, sorry, to point A, then back to P. When it's trouble. If one going from,
If one going, if when it's falling, it's still one together.
yeah, so it's going Q to P. And one going P to Q.
Yeah.
Right, but look at the resistor. Look at the direction it's going through the resistor. And it's going in the same direction, and it's going B to D all the time.
Oh.
So the voltage that we checking is the voltage through the resistor. Right? So the voltage through the resistor is that one on the right hand side here. Right? This is the voltage through resistor. Are you okay with that? Next smoothing. Head up smoothing, right? Head up smoothing. I wouldn't make it joint again, but really and truly. Right? In smoothing, you have to add something for a capacitor. And you can on the light. Check on the light. Check on the light. Easy. Right. So what you say? Here's how this works, right? The problem is although it now all in the same direction, the problem is that it's not constant. Right? So the problem is it should be smooth. That's okay? So if you all look at it right now, it's all in the same direction. But you don't want that, right? You want a constant supply. So we're going to use a device called a capacitor. Right? This module one of them. I didn't show you this as yet, right? A capacitor is a device that stores charge. So here's how it works. Right? We have our same circuit. Right? I just do a little block diagram there, you don't have to draw it, right? And to that circuit, we include a capacitor. This symbol here is a symbol for capacitor, two parallel plates. All it does, it will store charge and then release the charge. Just like when you charge your phone, right? The battery like a big capacitor. Will store the charge and then while you're using TikTok and then they're using the charge. Yeah.
How do you do the interaction?
Yeah, capacitor plus and minus.
So if you recognize it just compared to itself.
You just you are to lay it. But for now it's not simple. But you have to lay it plus and
So how?
you put plus and you put minus.
Just anywhere.
Any side. And this way, any side. Right? Here's how it works. Watch the blue line, right? Ignore the red. The red is the full wave. Right? So the red is what kind of going into the capacitor. So here's how it works, right? During the first phase here, it's going to the capacitor and it charging the capacitor. Right? When it reaches maximum here, right, the capacitor fully charged. So instead of your voltage going down, what I will do is I'll trigger the capacitor to come on, right? And the capacitor will start to give off a charge. That's okay? So this part here is not happening anymore. That's okay? And while the capacitor giving off a charge, it's charging up, it's going to start back charge again. And then when it reaches the highest point, it will repeat the process again. That's okay? Then it will charge again, and then when it reaches the highest point, it will discharge. That's okay? So the shape will look a little more like this. here we're getting smoother and smoother. And all you have to do is to make sure it's a straight line, is use a large capacitor. So it means that it's always going to have enough charge in it to keep it constant. Okay with that? So all the capacitors going and do is every time the voltage starts to drop, it will release a charge. Right? And it will keep it constant. Okay with that? The bigger the capacitor, the smoother it will be. So this entire process is called smoothing. All right. So now we officially have our AC converted into a DC. That's okay. Do me a favor, copy that down here. AC is a DC. I know some of you all won't see any holidays, but I kind of want to review a quick little summary on what we did during the holidays, right? Might be lost. Huh?
Yeah, very bad.
And then we added the element next. So do a lot of information. Right, all the module doors. When you upload the after the lights, you are to go behind it.
That's what
Would you like
Oh, you was there. That was something very complicated. I realized.
Okay. Yeah, well, So they didn't know any current state of affairs. Why not there? Online, you're seeing this?
It's under the. Hey, I was going out to like out.
Ready? All okay online, Shania? All okay? Aria? All okay?
Yes, so my tree. Yeah.
All right, can I take it off now? All right, so this brings us to the end of module 2. For those who were here from July. We got it. So, right, so what I want to do is give you sorry? Right, so I want to give you a small summary now on what we did. Module 2 summary, just now after. Yeah, module 2 summary, you don't have to write, I can send you the summary, right?
This week.
All right, so let's take a look at some that in the holidays. As I said, I will send you this, right? Everything here is what we did in the holidays. And now as well, right? Right, we did alternating currents. But we did that today, we did the diodes and all those little things, right? During the holidays, we did digital and analog systems. Right? This was the analog, you remember it, op-amps? Even if you don't remember, right? This is our op-amp, right? This is the op-amp, and the op-amp, those on the right hand side here. This was the everything here, like the properties of the op-amp. What I'll do is I'll take a day or two and I'll try and I don't think it up.
Yes. It will inside of
Right. So one of the things that we did, we did something called. Let's start here then. And I'll do analog money board. Right? Let's start here. So the first thing that we did logic gates, those are all the gates I should know, right? And then we did how to convert all the gates. I'll give you this handle. right? And then we looked at taking the gates, all these gates here, and making them with NORs alone. So here's the example of all the NORs, right? So if I wanted to make a NOR gate, right? Take a NOR gate and make a NOT gate. Or sorry, that's a NOR gate, NOT gate is here. Right? This is the OR gate, the AND gate, and NAND gate XOR. All those gates have NORs made up of them alone. I can also take a NAND and make all the gates. Right? So you have to learn all of this. Remember this? Right? So I can make any gate using a NAND. I can make any gate using a NOR. You have to learn that, right? Yeah. And then we learn how to do addition. So we said that for us to do a binary addition, we need something called a half adder and full adders. Half adders can only handle what? 2 inputs, and the full adder can handle 3 inputs, right? And I showed you how to use a full adder and a half adder. Right? So for example, here we have binary addition. Right? We have binary addition. Binary addition involves the adding ones and zeros, right? Anybody remember how to build an adder chip? What do I need to build an adder chip? One half adder, 2 half adder. How much full adders? 2. In this example here? 3. So 1 half adder and 1, 2, 3 full adders, right? So we need that to build that adder chip. Right? Here's an example of an adder chip, right? And I'll show you how it works. A next application of this gate was something called flip-flops. Right? We have a NOR flip-flop and a NAND flip-flop. Anybody remember the major application of flip-flops? As an alarm or to save, right? To save. Right, but clock is this one here. That was the one where they keep switching the inputs, and then you can change the output, right? Like a T-type out, like a T-type. All right. So all those things there was the logic. Sorry, was the digital part of module 2. Right. I want to go over the analog part of module 2. Right, before you give some multiple choice, right? Right, so the analog part looks like this. Right, remember all these videos there, you have to spend some time on go over some of these things, right? Right, analog. So here's how simple the analog was, right? Ariane, you can tell what you know, right? So basically, here's how it works. The analog signal, it takes a low input and gives you a high output, right? So it amplifies. So that's how we call it a op amp. Okay? How much it amplifies? How much it amplifies is called a gain, right? They take the input and they take the output and they divide them. Right? So you divide output and the input to get the gain. Look at that. Look at that. Right? And then the op amp looks like this. What was the op amp made of? Remember how to show it? The op amp was a little triangle, that was a transistor, and it had what? It had 2 inputs. It had a inverting and non-inverting. It had a supply, a positive supply, and it had a negative supply. It had an output, and it had 2 inputs, right? This is inverting, and this is non-inverting, right? Nalia, do you remember the problem that we had in the output was too large? What is called that? What is called when the output too large? Saturation. Saturation, right? So the output the output has to be between two values. The output has to be between negative VS and. So the output has to be between these two values. If the output outside, right? Otherwise, it is saturated. All right, so the output had to be between those two values. How you find the output? You can rearrange this formula, and you can get output to be gain by V. And then we had three types of op-amp. What it was? What were they? Three applications of the op-amps. Number one, we had a comparator. We had a comparator. Right, the comparator basically looked like this. And then we had inverting. How you know the inverting? Yeah, anybody something else missing? Something else missing as Daria. How you know the input? How you know it? It has feedback resistors, right? Right, there was one here, RF here, and RI here. Okay, and which one larger? Right, RF is larger. How you find gain again? No, for inverting op-amp minus RF on RI. And then you have non-inverting op-amps, right?
Yeah, that's nice.
Right, and you add non-inverting op-amp. Yeah. VCC is like high. That's like a 1. So you have two things. You have VCC, which is high, and then you have third symbol, which is 0. So yeah, the highest voltage. And this is like the lowest, what is 0. Right? And how you can gain here?
R1 plus RF on RF.
Sorry?
1 plus RF.
1 plus RF on RF. Well, I'm using RF on RF. That's okay? Right, of course, I'll give you this summary here and outside. I'm going to add the other people outside.
Like these pictures, this picture.
Right, let's take a look at some of All right, so let's give it a little try. I know you might be able to do everything, but I still had a review, right?
I don't think that's a single picture. I do think.
Alright, let's start. Let's start here. Take a look at number 16, and we're trying to. No more time. Right, at the time in the 80s, I'm stop picking on something, that's one of the years.
She like 10 seconds.
Ah. It's in the back. Alright. At a time. In an AC cycle, when the terminal X is at a negative potential, means here negative. It means that here negative and of course here positive. Y is positive, which diodes will be conductive? Take your time, take your time. It's 20 something, right?
Nice.
Write down 16 and what you think the answer is, right? Huh? We look at this. Yeah. Online, your message. What you all think? A, B, C, or D? What you all think? Boy or dog? Dog. Alright. So let's see. What is here? It's negative, right? So to make it easier, those start at X, start at Y, right?
Yeah.
Current going this way. So will it go to Q or S? Will it go to R?
No.
And where will it go here? Q or P? So the answer is S and Q. 500.
Sit on my side.
Right? Are you okay with that? Dog?
Yeah.
How about the small? Everybody okay with that? Online, Kyra? Are you okay with that online? Oh, it's somewhere. Next one. 17. Let's stop that now. 17. Which of the following materials does the IV graph best represent? What? Why is it diode?
Because it's just
Right, because little on nothing to the left side, right? Very good. You answered cut. Next one, number 18.
I think so.
Number 18, yeah, you formula from last week.
Yeah.
How you find root mean square? We did that last week.
Oh, I don't remember.
How much you got?
3.54.
3.54. Right, so V RMS is equal to V naught plus So that is 5 on root 2, which is how many is that? 3.54.
5-4.
Anthony, you give it up?
Well,
Nobody worries, I don't start. Alright, let's go again. I think that might be the last one. Or remember voltage. Alright, ignore this one, right? Because it might do something. Thing to work it out. Right, 20. Look at 20. Look at 20. What kind of pump is this? What kind of pump is this all here? This is a non-inverted, you sure?
yeah, it's an inversion of a.
Inverted pump, right? And the input is what? The input is sinusoidal. So which one here is the output?
The bottom one. C.
One answer. See, think about it.
Let's see what these circuits are inverted. No, the answer is D. D. Yeah, D.
Or A or B.
No, it can't be A or B.
Why it can be A or B,
It's inverted
right? And why not C?
because C is going 15 to 6.
What is 6 to 6? 6 to 6.
Oh,
Right? So the answer is
D.
dog, right? Right? It's an inverting, so it means that positive will be negative. So you see it inverted here, and the largest possible is 50. That's okay? So the answer was dog there. If you remember it, 21.
D.
Hey, you want to spot here, tuning her lip?
I wasn't in it.
I got you, you here tuning her lip?
Sister, I say every day.
I can't say something. Alright, that's two, right?
Yeah, she was here every day.
But she wasn't here.
Yeah, I was. Dog. Said I wasn't there. I had a thing to do. You know something else.
Alright,
Somebody.
alright, watch this here, next one. The open loop gain of an op amp is very high. However, its bandwidth is narrow. This means that what?
Take you up, but I don't small value. Oh, is that you?
That says door. Right, remember, if you,
I did it, so I want one time.
right, if you remember, what's the shape of that graph? Gain versus frequency. It was shaped like this. That's okay? And down here is frequency. So the higher the gain, the smaller the frequency, right? That's a high gain, down here is a low gain, so the frequency is larger. So the answer is dog. Right?
Yeah.
The answer is dog, right? Which of the following are properties of an ideal op amp? Grant you, if you're hearing a list,
We do it in class yesterday.
22. Shabish, 22. Shabish, you were here during the holiday.
I didn't have it, so
So, okay. Huh? 1 and 3. Which are the following properties of an ideal op amp? Zero outputs,
yeah, 1 and 3.
zero impedance, correct? Infinite input impedance.
I think it's 1, 2, and 3.
No, one of them.
Yeah.
Start with module one.
1, 2, and 3. So the chance that
Module one. Yeah, so 1, 1, 2, and 3, right? Zero output, infinite input and infinite output. All right. So the answer is dog here. Anybody remember this one? Why is called this circuit? Nah, more specific than that. Actually, you know you're supposed to get that right.
Yeah, because
No, but I know the actual answer.
that's so many.
No, how is that summon? Summon has more than one input.
A voltage follower.
But you just call everything. Yes, the answer is apple, voltage follower. But yes, it is a non-inverting upper. Right? Huh? Yeah. It's maybe one that top.
Oh, but so that's what
It is a non-inverting, but the best answer is voltage follower. That's the actual name of it. But it is an example of a non-inverting. Next one. The value for the resistors may be changed. Which of the following pairs give the largest bandwidth? Largest bandwidth comes with the smallest.
frequency.
No, gain. Right? Largest bandwidth is smallest gain. Oh, by the way, did we agree on module 1 or 2 videos? One. Right. Smallest gain. Right? Which of those values there will give you the smallest gain? A. Whatever op amp is the estimation. Whatever op amp is that. Right, you can't take all one.
So we did figure it out. Sure, this one out. I didn't even have many some vacations.
Yeah, Shivish, whatever op amp is that. Huh? You wasn't here? Shivish. Inverting, right? And how you find gain for inverting? On the board. Huh? Clear? Minus RF on RF. So the formula for gain minus RF on RI. Which of those is give you the smallest?
D.
Which one?
D.
This one here is 2, this one here is 3,
That one is 10. That one is
there's 15 and then 10. So the answer is
D.
dog. Right? The answer is dog. Next one.
This will give you
What single gate is that?
no
A no?
EXO.
EXO.
So she got it right.
EXO. Alright? You have to learn that, right? Alina, you were here? You know it?
Alina, what's your everyday?
Right? 25 was dog. Alina. What is somebody else? Who? Nishara. Azaria. You were here, Azaria. Well, you shall be here for. Right? What type of amp is this earlier?
Inverted.
It's an inverting summing amplifier. Right? See if we can figure out which one is the answer then.
So I just like I think it's very I get it. Yeah. That's what I was.
How you find it? The formula is this divided by this. Right? So it will be minus 20 on 5, minus 20 on 10, minus 20 on 2.
So why will I use it?
Huh? RF on all of them. What's the answer? Check it fast.
Oh, yeah.
Yeah, -4, -2, -1. Alright, C. Okay? No. All remember this?
Yes, sir.
And diagram above, current flowing is an N type, so electrons moving from where to where?
From I to B. Where is it longer, like?
Electrons will move from where? Q to P or P to Q,
It's the Q.
right? Because
Longer line.
electron going next way, right? Q to P. So the answer is cut. Next one, look at this here. It's going into OR gates. See if we can figure out, you should be able to do this, right? Because you remember Form 4 physics.
What we gonna do?
1 1 0 0 0 1 0 1. Right? This is going into OR gates.
I'll get this song now.
OR gates.
0 1 0
Huh? 1 1.
0
Very good. Tell me which one is that? Which one is 1 1 0 1?
B.
Boy?
Yeah.
Nice.
Good job.
Good job. Figure out this. This is Form 5 physics. Figure this one out.
Right, 1 1.
What type of logic gate is represented here?
Hey, it's 1 1. 0 0.
No, wait, hear what they're saying, right? They say that the electrical circuit above can be regarded as a logic gate. What type of logic gate is represented there? That's a slide, man.
Oh yeah. Teacher said he doesn't get to show on the
When are you doing it too?
Yeah, we go right. You don't.
Yeah.
You don't.
What gate is this? Huh?
No, if it's not knowing, we have to be 1.
For the circuit to be on, what must happen?
Yes.
Two are to be closed, then?
And
Which one is that?
Not.
AND gate. Only an AND gate behaves like that, right? Only an AND gate behaves like that, right? So the answer is apple. And last one. What's the answer here? 1 plus 0 plus 1 is what? 1 plus 0 plus 1, well, it's 2 and can go to binary. What's the answer? One plus 0 plus 1 is what? 2, right? So which
is 1 0. Because
Huh?
1 0.
is apple?
Yeah, because it's about carry.
Right? Because remember, in the notes I gave you, I put carry first.
Oh.
So it would have been easier, right?
So that's why.
Apple is the answer, right? Apple is the answer. Alright. So that was real bad. You also remember anything. Alright. So that was module 2 there, right? So I'll have to spend some time on Google that someday, right? Yeah. So alright. What to do? Analog in 15. Alright. Next day we want to focus on module 1, right? So let me just give you an idea what module 1 is about. Huh?
Yeah, direction.
We Stonebridge, yeah, we did that. We Stonebridge, I'll light up. Right, I'll send this in the group together with the summary for module 2, right? Right, budget yes. So your module 1 has to do with electrostatics, electricity, and then magnetism. Alright, so it's made up of those 3 things. Right, saying magnetism.
Yeah, magnets. Where are the magnets?
Anyway, I can't remember.
Magnets, what do you want?
But it came for exam this year. What is it for?
That's
Right?
That's true.
The first thing in electrostatics, we could do that now actually, yeah. Yeah, let's start one time. I will read because I will have to read it to homework and it won't do it. So I'll do it now.
Oh, you're ready to go, sir.
No, you will not.
I promise, yeah.
Right? You don't have to write it. This is Form 5 one. Right? Yeah. So the first part of electrostatics, you don't have to read it. I mean, you don't have to write it, right? Alright. Well, let's just run through this fast and be done. Alright? So the first part of module 1 is electrostatics. You would have done that in Form 5. Where we talk about the 2 kinds of charges are what?
Positive and negative.
Right? A positive charge. If you have to define an electric field is what? A region of
Space.
right, a region around the electric charge where we have force experience. So if I have an electric charge here, an electric field is the region around it where you will experience an electric charge. Right? We have to find the strength of that electric charge and so on, right? Right, but let's take a look at what we have here. Positive charge, negative charge. Oh, before continue, anybody remember the direction of the electric field? It goes somewhere to where? It goes from positive to right? So the electric field, the direction is always from a positive charge to negative charge. Okay? So we have to know these little things here. Types of charges, plus and minus. Right? Fundamental charge and charge of an electron, 1.6 by 10 to the minus 19. An electron is minus 1.6 by 10 to the minus 19. Sometimes I'll just use 1e, right? The charge of proton, positive. Like charge is what? Repel and unlike charges. Anybody remember how the P lines is look? Right? So the P lines are wrong, a positive look like this. That's okay? The P lines are wrong and negative look like this. Right? Like charges will look like this. That's it. Caroline. Should be like, right? Like charges look like this because they do interact. And unlike charges look like this. That's okay? Oh, that's Form 5 stuff, right? Right? We have 2 ways to receive a charge. Charging by friction and what moves? The electrons actually move, right? So as you rub one material, the one electron will leave from one and go to the next. Right? So charging by friction is a little more permanent than charging by induction. Right? So if you look here, we have an example of charging by induction. You're seeing that? The metal spray has no charge. When you bring a positive charge next to it, the electrons are attracted on one side, and to the opposite side, you have the positive charges. That's okay? And then when you remove it, it's not permanent, so the electrons and the protons are equally distributed. All right? Anybody remember the applications of this? Right? So here's one example, an electrostatic precipitator. Painting a car, agricultural spraying, right? And the electrical photocopier. The that's the first one I'll show you. Something else that I did a lot in Form 5. Well, spent some time on in Form 5. The lightning rod. Remember that? The lightning rod. And here you have some examples of some examples where electrostatic conduction bar, right? Aircraft, fuel tank, anybody remember they put them in aircraft without reading it?
So when I fly and,
Huh?
it can cut off the whole plane.
Right.
Yeah.
So electric charges may accumulate due to frictional effects between aircraft and air. When the aircraft lands, the discharge is potentially explosive in the presence of aviation fluid, right? Aircraft are therefore made with slightly conducting rubber so that the charges are conducted harmfully to when the aircraft lands, right? And then the lightning rod. So I want you to read up on those things when I send it, right? I'm gonna send it now. Right, I'll send it now. So next day we start with electric fields, right? And the major application of electric fields is the capacitor. So you're gonna spend a lot of time on the capacitor.
No problem.
Alright? Alright, we'll stop there for today. Next day we officially go into module 1.
No, maybe they said about this.
Big letter.
Thank you.
Alright, right online.